Hi guys, so we are going to finish up the slides that have to deal with electronegativity and polarity. With these slides I gave you a handout today before you left and it looked like this, so please make sure that you have this handout while you are looking or watching this video. I'm going to try to go as fast as I can because I know some of you are in Macbeth and I want to try to make this as short as possible for you, okay? So whatever questions you have, write them down, email them to me, post on the blog. I'll try to get as much stuff as I can answered tonight if you want those questions answered tonight, okay? So we left off on this slide. We left off on determining polarity of molecules. Now, we know that we can determine if a bond is polar or nonpolar, and that's just specifically looking at bonds. We also need to determine if a molecule, an entire compound, can be polar or nonpolar. We can do that by looking at the shape of the molecule. When we look at the shape of the molecule, you know that the molecular geometry is dependent on two things. It's dependent on bonding domains and non-bonding domains. So it's really important when we determine polarity of a molecule. So we've been looking at polarity of just bonds. So if we're looking at polarity of just bonds, that's what we did today. We are now looking at polarity of an entire molecule, okay? So polarity depends on the shape of this molecule. When the charge distribution is unequal, because the molecule isn't symmetrical, asymmetric, the molecule will be polar. I want to give a few different examples of why shape will determine polarity of a molecule. So on this one I gave CO2 and H2O, and I told you whether they were nonpolar or polar. So let's look at why one is polar and why one is nonpolar. Okay, so actually before we start with those examples, I first just want to start with a really simple compound. Let's just say we have HCl. Based on my knowledge of electronegativity, I know that Cl is more electronegative. So that means the dipole, which means partial charges, remember, the arrow of that dipole is going to be pointing towards chlorine. Why is it pointing towards chlorine? It's pointing towards chlorine because chlorine is the more electronegative element of these two. So if this is my compound, which actually this is just one single bond here, but this could be a compound or a molecule. So in this case, is this molecule going to be polar or is it going to be nonpolar? This is going to be a polar molecule. This is a polar molecule. This is polar. A really easy way to think about this has to deal a lot with being symmetrical. If I only have one bond and I only have one dipole moving in one direction, there's nothing that's there to really cancel out this dipole. So that's why this is going to be considered polar. Now I want to look at the example that I had, CO2. That was one of the examples that was on that slide that we just looked at. When I draw CO2, when I draw the Lewis structure, because I have to figure out the shape of CO2. So carbon dioxide, carbon will be my central atom because it's the least electronegative, and then it's bonded to surrounding atoms, which are oxygen. And I know that oxygen needs to have, or the surrounding atoms need to have their electrons filled. So I could do that. Oh, wait. Okay, hopefully those can be seen way easier. I know you said, guys, that you couldn't see those little dots that I had before, so hopefully that helps. So now if I look at oxygen, I see that each oxygen has 8 electrons around it. But if I look at carbon, I can see that carbon doesn't have that fulfilled octet. So I could calculate formal charge here and see that carbon is actually not a formal charge of 0. So I'm just trying to speed this along, guys, so that way we can get to determining the polarity of the molecule. So oxygen is actually going to donate this lone pair as being a shared pair, as a covalent bond. That one is going to go there. So I'm going to redraw this with a double bond. Okay, so this is what I have right now. I'm going to erase the rest of it so that way we don't have any questions here. So this is my Lewis structure for carbon dioxide. I now need to figure out the shape. So I know that there are electron domains around this carbon. How many electron domains around carbon here? There are 2. You have one here, you have one here. If there are 2 electron domains, what is the shape of this molecule? There are 2 electron domains. That tells me it's linear. So this is a linear shape. Okay, so now I want to add dipoles to this because I need to determine if I look, let's forget about this O for a second. Let's just look at this C and this O. If I look at these bonds here, which one is more electronegative? Is carbon or oxygen? We should be saying that oxygen is more electronegative. So I'm going to draw my dipole here. Now I'm going to look at this bond. I have carbon and oxygen. It's the exact same bond. It's just that now oxygen is more electronegative in this case. So this arrow is going to go this way. So I have a dipole going this way in this bond, and then there's another dipole going out in the opposite way for this bond. So overall, I consider carbon dioxide to be nonpolar. And I consider it to be nonpolar because this is symmetrical. This is symmetrical. The dipoles are moving in opposite directions. So it's kind of like they're canceling each other out. So because these dipoles are in opposite directions, they're canceling each other out. Let's look at another example of where they would be canceling one another out. So like CH4. Very simply, I know Lewis structure for carbon tetrahydride would be this. So I see carbon, 4 hydrogens around. If I wanted to determine the electron domain geometry, I know there are 4 electron domains. 1, 2, 3, 4. And so that tells me the shape is tetrahedral. If I think about the molecular geometry, there's 4 bonding, 0 non-bonding. So that tells me it's still just tetrahedral. Now, I need to determine what dipoles I have, or if I have any partial charges anywhere, if I have anything at all. So carbon and hydrogen. If I look at carbon and hydrogen, we did this bond together in class today. Carbon has a 2.55, hydrogen has a 2.2. When we found their electronegativity difference, we found that this bond here is actually nonpolar. So this is nonpolar, this is nonpolar, this is nonpolar, and this is nonpolar. So I don't even have any dipoles here. I don't have any partial charges that are created in this compound. That makes it nonpolar. Let's look at another example. Let's say we have CCl4. Now I have carbon tetrachloride. So again, carbon is the central atom because it's the least electronegative. I'm going to draw all of my lone pairs on chlorine. Okay, so in this case, I can look at carbon and chlorine, and I know chlorine is way more electronegative than carbon. So am I going to have a partial charge here? We will. We're going to have dipoles here. And each of these bonds are the exact same. So once I look at the bond for one, it's like I've looked at it for all of them. So in this case, carbon and chlorine is more electronegative. So which way am I going to draw the arrow? I'm going to draw the arrow toward chlorine. If I look at this case, chlorine is more electronegative. There's a dipole. That means that the electrons will be more around chlorine. You can actually see that, guys, too, in the Lewis structure. You can see that chlorine has way more atoms surrounding it because it wants those electrons. So the electrons in this bond are going to be more facing towards chlorine. In this case, I have carbon and chlorine. Dipoles this way, dipoles this way. Okay, I have 4 different dipoles here, and I need to determine if this molecule overall is polar or nonpolar. I have 4 different little polar bonds around here. I see that. But these two are acting in the same direction, or these two are acting in the same axis but in opposite directions. These two are moving in opposite directions. So it's like they're canceling one another out. So that means that this overall molecule we would consider non-polar. Certain geometries will have specific polarities. So you actually don't even have to go through this process if you don't want to. You can actually just remember based on this page that I gave you here. So if you look at this page, I see on this first row, it says number of electron groups. That's 2. And then it says type of electron pairs. It says 2 BP. Tells you up here BP means bonding pair. So there's 2 bonding pairs. That's what it looks like. So we know there's 180 degrees there. It tells me the polarity is nonpolar. And we just looked at one like that. We looked at carbon dioxide. Carbon dioxide is nonpolar because those dipoles moving in opposite directions cancel one another out. So it's kind of like that partial negative and partial positive charge, and this one is canceling out the partial negative and the partial positive charge of that other one because they're in opposite directions. So any linear molecular shape will always be a non-polar molecule. If you would look down on that group where it says number of electrons and find 4, look at the tetrahedral group. Here's 4. I have 4 bonding pairs, so this is tetrahedral. It's nonpolar. We just did that one. Carbon tetrachloride is tetrahedral. We know that because there's 4 bonding domains here. You just determined that it was nonpolar because these 2 are going to cancel one another out, and these 2 can cancel each other out. It's like, again, we're canceling out those partial positive and partial negative charges. So if you look on that paper, it tells you 4 electron domains, 4 of those are bonding pairs, it's nonpolar. So any tetrahedral molecular geometry will always be nonpolar. Now the rest of them on that page you see are polar. So let's look at an example.
Casey Abrams, if you're in the building, would you please call 10029? Casey Abrams, please call 10029.
Sorry guys. If you want to determine if something's polar, then we're going to let's look at an example. Like H2O is a good example. Okay, H2O, for just time's sake. Water looks like that. That's the Lewis dot structure, or the Lewis structure for water. Now, I look at the electronegativity difference between oxygen and hydrogen. Oxygen is much more electronegative. So that means the dipole is going to be moving toward the oxygen. In this case, it's going to be moving toward the oxygen. Are these moving in totally opposite directions? No. They are moving toward the exact same spot. They're moving towards one another. Plus, oxygen has these 2 lone pairs on it as well. So there's all of these electrons that are trying to be surrounding oxygen. So nothing can really cancel out here. In this